Good afternoon, guys. Can you hear my voice?
Good afternoon, sir.
Okay, let me share my screen. Is my screen visible?
Yes, sir.
Okay, we'll wait for 2 minutes. Just 23 students are there. We'll wait for just 2 minutes and we'll start the class. All right, so let us start today's class. Let me revise what we started discussing from the previous class. We started discussing process management. We try to discuss what are the various states in the process management. Like once the process is started, it will be in the new state, and once it is ready to admitted, it will be kept in the ready state, and from ready state it will be scheduled for the processor to execute. And once the process is executing, then it will be in the running state. Once this state is finished, then it will exit and terminate it, or in between, if the process needs some input output event, it will go into the waiting state. After finishing input output completion, again it will be kept in the ready state, and it will keep uh, uh, it will be kept in the queue for to be executed in the queue. And if some interrupts happened, again some that interrupts, because of that interrupt, again it will be kept in the uh, ready queue to be executed again. So these are the various typical states in a process will happen. We try to understand these are the details, and PCB is the process control block, which each process is represented by the operating system, contains associated information of what is the process state, what is the process number, what is the program counter, the registers that need to be assigned when it is executing, and the temporary files that need to be opened. And we understand also context switch. When a processor or operating system is executing from one process to other process, it has to save the process control block information before loading the other process information. So saving that information, loading an another process, uh, switching the CPU core to another process is called the context switch. We try to understand, and process scheduling, and we try to also understand the CPU scheduling. There are various criterias, but we try to study this CPU scheduling algorithms. Whichever comes first will be served first, and shortest job first, and shortest remaining time first. We try to study these three algorithms in the previous class. Like simplest algorithm is first come first serve, whichever the process will come first. For example, P1, P2, P3, we try to study that P1, if it is coming first, then it will be scheduled first for 24 milliseconds, then P2, then P3. If first come first serve process, if you go based on that, and this will become very bad if the process which comes earlier takes lot of time, because the waiting time will increase for the second or subsequent processes. We try to understand by studying a simple example, and if it is come first serve, only this will be very bad when the process which comes first, if it is taking more time, then lesser time, that lesser burst time process need to wait for a longer period of time, then overall the average waiting time for the system will be increased. That will bring us to a very bad throughput, because the throughput what we discussed is the number of processes that are completed per unit time or work done. The throughput is very bad if only one process is taking too much time and the average waiting time is increased, right? So we try to understand that in order to uh, we try to also understand there are two types of scheduling algorithms, which is non-preemptive and preemptive. Non-preemptive scheduling algorithms, in this algorithm the process will not leave in between. Once it is assigned or once it is started executing, it will completely finish. So FCFS is a non-preemptive algorithm, whereas preemptive algorithm, the process may leave in between, give for some other process to execute. That will happen in shortest remaining first, and uh, other priority based queue also. We'll discuss that today. Okay, so one of the best way to decrease the waiting time is to schedule the process which has lower burst times. Whichever has lower burst times, if you pick that and if you schedule them, then in turn your average waiting time will decrease. That also we try to study one example, and if the same example if we carry out in FCFS, it will take a lot of time, but whereas in shortest job first we took only 7 milliseconds. Shortest job first scheduling algorithm with the non-preemptive approach means the process is not leaving in between. We call that as shortest job first. The same idea, shortest remaining time with preemptive. The preemptive shortest job scheduling is also called as shortest remaining first. So in shortest remaining time first scheduling algorithm, uh, if the arrival time for a particular process, whichever has the less remaining time, based on that it will schedule. So we try to study process P1 is scheduled for 1 second, but at first second when P2 is coming to be scheduled, the burst time for P2 is less. P1 is 7 seconds. So P2 is scheduled because the burst time, the remaining time that need to be finished for P2 is very less. So P1 is leave before it's completing the work for that before completing the process. P2 will be placed. This is called preemptive algorithm. Shortest remaining time first is a preemptive algorithm. So P2 will schedule, then P1 will still wait because P4 is having lesser burst time, then P4 will be placed. Then after that P1, after that P2, P3, based on the burst time analysis. But it is also, we try to understand that shortest job first or shortest remaining time first, both of these approaches are practically not possible, because we need to have an idea of the burst time, that in advance, that we will never know in real time how much a process will take to finish time execution. We have to estimate it. We'll never know in actual time how long it will take. So predicting the burst time or completion time for a process, it's not reality. It's not the reality. So practically this shortest remaining first or shortest job first is not possible. Okay, so we try to studied up to this point in the previous class. So let us continue our discussion of CPU scheduling and process management in today's class as well. So as I told, this three first scheduling algorithms we finished in the previous class. Now let us try to study the round robin scheduling algorithm. As I told that first come first serve, whichever comes first you assign first. That would be the ideal case. But in this scheduling, the waiting time is pretty much high. Shortest job first, shortest remaining time first, they give better approaches. They give the average waiting time is less, but these are practically not possible, because to have that implementation, we need to have an idea of burst time, then only it's possible. But burst time, we will never be able to know what is the precise burst time for a particular process. Having studied this three approaches, let us now try to study the round robin scheduling. Round robin scheduling is very important scheduling algorithm, because this is the algorithm that we are using practically nowadays. Okay, so the round robin scheduling is similar to FCFS scheduling, but preemption is added to enable the system switch between the process. So in FCFS, once a process is assigned, it will not leave in between. But in round robin scheduling, the process is left, it can leave before it's finishing. A processor can switch from one process execution to the other process execution. But the catch here is, for changing from one process to other process, when a context switch happens, how, based on what a processor will decide to switch from one process to other process, is we call that as a quantum time, time quantum. A small unit of time called a time quantum or a time slice is defined. It will be vary generally from 10 milliseconds to 100 milliseconds in length, and the ready queue, whatever the queue that are waiting to be executed, is considered as a circular queue. Okay, so the CPU scheduler goes around the circular queue, allocating CPU each process for some time interval up to one time quantum. So for example, here assume that this is the same process where what we took, P1, P2, P3. P1 will take 24 amount of burst times. Uh, P1 take 24 milliseconds of burst times. P2 will take 3 milliseconds. P3 will take 3 milliseconds. Now what we did here is, for each process, we considered a quantum time or a time quantum. Okay, so at every 3 seconds, the time quantum we kept as 3 seconds. Initially, let us say that P1 is executed up to for some time. Then uh, after some time, P2 is executed. After some time, P3 is executed. Then again, P1 is coming, because okay, let me rephrase this. Here I forgot to add one parameter. I will add that, so that that will make clear. I told you here there will be a time quantum or time slice in the round robin scheduling. In this example, that is, I'm sorry, the time quantum is, I will write this time quantum, or let me do this. Let me add one point here. The time quantum or time slice is equal to 4 milliseconds. Okay, so time quantum or time slice is 4 milliseconds. So what happens? The scheduler will schedule 4 milliseconds on process P1, 0 to 4 seconds on process P1. Next 4 seconds, it will schedule on P2, but P2 needs only 3 seconds. After 3 seconds, the processor will be relieved. The next 4 seconds, it will spend on P3. Again, this needs only 3 seconds. So it will again switch back to the next process. So there are no next process. So next 4 seconds again, every 4 seconds, you see 10, 14, 18, 22, 26, 30. Every 4 seconds, a process will be executed and given chance to the other process. So process P1 will take only 4 seconds. Then it will wait. Process P2 will come and it will take time to finish its job. But before 4 seconds, before the time slice, it finished the job, so it needs only 3 seconds. Process P3 will come again. Process P3, the allotted time is 4 seconds, 4 milliseconds. but it only need 3 milliseconds, so it finished within the before time, then the processor will be available. There are no left out processes, so it will continue its execution. Is this make sense?
Yes, sir.
Okay, now let us calculate the waiting time now. So the simple is, for given time quantum, that each processor will execute a particular process irrespective of bus time. The bus time might be any value. Still, you will be able to, without the knowledge of bus time, you will be able to decrease the waiting time. Suppose this process, imagine, for example, I will tell you one example. So let's take pen. Imagine this is 5 seconds. What will happen now? Imagine P2, P3 will take 5 seconds. Now what will happen is P1 will spend 4 milliseconds on P1. So this is correct. P2 will also take 4, it will be 8. It will go to P2 will also take 4 milliseconds. So 4 minus 1, the remaining time will be 1. Here also, then it will go to P3. This is also take, the remaining time will be 1. So here P2 will take 4 milliseconds, then this will become 8. Then P3 will take again 4 seconds, this will become 12. Then again P1 will come. P1 will spend again 4 units of time. So this will become 16. Next again P2 will come. Now P2 will take only 1 second. So this will be P2. This will take only 1 second. So here it will be 17. Again P3 will come. This will take also only 1 second because only 1 second is left. So this will become 18. Then again P1 will continue to execute. Does this make sense?
Yes, sir.
Yes, sir.
So round robin scheduling algorithm considers this process in a circular form. So how circular array we discussed, you remember that at the time, if you recall, I told you that round robin scheduling algorithm takes efficient way in order to decrease the waiting time. Now for this original example, let us calculate the waiting time. So P1 waits 0 milliseconds, but here 10, after that it started, its time came after 10, at the 10th millisecond. So 10 minus 4 will be its original waiting time period, will be P1 waiting time 10 minus 4, that would be 6 milliseconds. P2 waited 4 milliseconds, P3 waited 7 milliseconds. So the average waiting time is 17 divided by 3, 5.66 milliseconds. The same example that we discussed in FCFS. If it is FCFS, what is the waiting time? In FCFS, what is the waiting time? If you go straight away with non-preemption, FCFS will take, if you come first sir, process P1 will wait 0 milliseconds, process P2 will wait 24 milliseconds, process P3 will wait 24 plus 3, 27 milliseconds. So what is the average waiting time? 51 divided by 3. This will give you 7 3s are 21. Okay, 17 milliseconds, correct?
Yes, sir.
But because of round robin scheduling algorithm, the same approach we could able to bring down to 5.66 milliseconds. These both are not having the knowledge of bus time. Without the knowledge of bus time, we could able to efficiently bring it down to 5.66 milliseconds. So this is the algorithm that in our real life now the round robin scheduling algorithm is executed with some additional features that we will try to see. But uh, we need to have an efficient way to decrease the average time without the knowledge of burst time uh, to have a real life scheduler. So round robin scheduling with a circular queue is one of the best approach that has been proposed. Is this clear?
Yes, sir.
Anyone has any doubts in this? You want me to repeat the scheduling algorithm? Shall we go ahead?
Yes, sir.
Okay. So we will also see one more scheduling, then we will switch back to the process management. So there is also called a priority scheduling, because I told you that there will be always priorities. The priority is associated with each process, and the CPU is allocated to the process which has the highest priority. Equal priority processes are scheduled in first come first serve order. Shortest job algorithm is simply a priority algorithm where the priority P is in the inverse of the predicted next CPU burst. Uh, what is this meant to say is shortest job first algorithm is also one way of priority algorithm, and we are giving the first priority to the burst time which is having lowest burst priority, right? So that is what it meant to say, that the priority is higher to the lowest burst CPU. That's what we study, shortest job first. Whichever burst time for a particular process is very low, that will be given highest priority. That's what the priority is, the inverse of the CPU burst, or predicted, whatever the predicted next it is going to come, that will be the inverse, the highest priority will be given to that particular job. So the larger the CPU burst, the lower the priority, and vice versa. Priority scheduling can be either preemptive or non-preemptive. The major problem with the priority scheduling algorithms is indefinite blocking or starvation. Why? What is indefinite blocking or starvation is, for example, imagine that you are the lower priority job. If it is a preemptive, if it is a preemptive, uh, then what happens is the priority jobs which will keep coming, and they will keep taking the execution by the processor, but the lower priority jobs will keep on waiting for their turn. Okay, imagine that you came to cafeteria, you are waiting in a line. Let us say that the director sir came, and because he is having highest priority, you waited in the line and you let him go first. Then after register sir came, then again you waited and you allow him first. Then imagine the dean of academics came, you allowed him first. Dean of student welfare came, you allowed him first. Then head of the department came, you allowed him first. People with having higher priority, they keep coming. The people having low priority will have to keep waiting on the backside. They will keep coming and they will keep getting their job done. But what about the lower priority people? And such case we call that as a starvation. Okay, the lower priority jobs, the major problem with the priority scheduling is the lower priority jobs will never get their chance. People with higher priority will keep coming and taking the time that they got allotted, and that is the main problem of the starvation. Is this make sense?
Yes, sir.
Right. Okay. So let us discuss again with some example. Let us assume that we have process P1, P2, P3, P4, P5. We have burst times. Also, we assign with priorities. There is another additional priority, additional parameter called priority. Now we will schedule the process which is having as per the priority. So priority 1 is having P2. So P2 will be scheduled first, irrespective of their burst time. Based on the priority only, we will schedule. So P2 will be scheduled first. Then second priority is P5. P5 is scheduled second. Then third priority is P1. P1 is scheduled. Then fourth priority is P3. After that, P3 is scheduled. Then last fifth priority, P4 is scheduled. Calculate the waiting time for this scheduling. What is the waiting time? What is the waiting time for process P2, first priority process? It is 0, right? It did not waited for any amount of time. Directly it went and it started its execution. Second priority, how long it waited?
1.
1 millisecond. Okay. Next, third priority, how long it waited?
6.
This is the burst time is 5, and the P2 burst time is 1. 1 plus 5, 6. So P1 waited 6 milliseconds. Okay. Then what about? Sorry, is that correct? Yes.
Yes, sir.
Okay. P1 waited 6 milliseconds. Then what is the fourth priority? P3. P3 is the fourth priority job. How long P3 waited?
16.
6 plus 6 plus 10.
70.
Okay, 16. Then P4 waited 16 plus
Sir, 18.
16 plus 2, 18. Sorry, I'm writing with mouse. That's why it is not coming clearly. What is the total? 6 plus 16, 22 plus 18, 40, 41. Correct? Six plus 16, 22 plus 18, 40, 41. Correct. So 41 divided by 5. What is the answer? 8.2. That's it. Okay. So 8.2 milliseconds. Is this clear?
Yes, sir.
Yes, sir.
Okay. 8.2 milliseconds. Yes, we got the correct answer. Right. So these are the various ways. Suppose if it is a preemption, so let us suppose that after finishing P2, after finishing say second priority job, let us imagine P6 is coming with bus time 3 units with priority again 1. Then what will happen?
P6 will get executed.
Then after we will check whether it is executing or not. Depends on the arrival time. If you have the arrival time, you check the arrival time when it is arriving. Based on that arrival time, uh, whichever the process is having higher priority, the lower priority will leave, the higher priority will keep scheduling. If the arrival time is not mentioned, then after finishing this P5, then the next job will schedule is P6, because this is having again highest priority. Okay. Guys, confused? Am I confusing or is it clear?
So please
Yes, sir.
repeat.
Sir, please explain one more time, sir.
Okay. See here, the arrival time is not mentioned clearly. Imagine that arrival time is 0 for everyone. Okay. We are assuming that we are not talking about arrival time. Suppose the arrival time comes, arrival time is there, then things would get little much out of hands. Suppose say that, okay, let me start again. Let us say that we will consider arrival time. Okay, imagine all this is coming at 0 milliseconds. I wish I could have a board. In board we could have discussed a lot of things. In writing, mouse, it's pretty much difficult. Anyway, assume that this is arrival time. Okay, please forgive me for this mouse writing. Okay, so arrival time is, assume that this is 0, 0, 0, 0. Imagine this is 0. Now there is another P6 is coming at third millisecond. The arrival time of P6 is third millisecond. Okay, the burst time, let us take, it is only 1 millisecond. It will take, or one, whatever it is. The priority is 1. Now what will happen? The arrival time is 0. At 0th position, you will schedule what? For all these 5 processes, arrival time, there are no process available. So since arrival time is same, you will execute whichever is having the highest priority. Which is having highest priority? P2, right? P2 is
Yes, sir.
scheduled. P2 is scheduled. This is 1 second. Next, what is the highest priority? 2, right? At arrival time 0, 2 is coming. Next highest priority is P6 with having priority 1, but the arrival time is only at third millisecond. Okay, so till third millisecond, the process no need to wait. It will allocate P5. P5 will be allocated just for 1 millisecond. 1 millisecond is finished, so it will come at the third millisecond. So P5 is allocated for 2 milliseconds. P5 is allocated for only 2 milliseconds, so this will be 3. So minus 2, this will be, the remaining waiting time is 3. At the third millisecond, what will happen? So processor spent 1 millisecond on P2, 2 milliseconds on P5. A third millisecond, P6 came. A third millisecond, P6 came. Now the priority of P5 is 2. Priority of P6 is 1. Which one it will execute now?
P6.
P6.
P6 will execute. So process P5 will wait. It will leave. Then P6 will come. P6 is allocated. Then it will finish its highest priority. Minus 1, it will become 0. Then it will become the waiting line 4. Then after 4, again, which process will resume?
P5.
Again P5 will come. So again P5 is scheduled for next 3 seconds. Okay, then that will become 7. Okay, this is Gnan chart. We are making a different Gnan chart. Okay, this is called preemptive. This is called preemptive. Okay, is this clear?
Yes, sir.
Now imagine, now at P7th second, there is a process P7 at arrival time 4. Again a burst time with 2 with priority 1, it came. Now after P6, which one will execute? Why? Because the priority is 1. At the fourth second, again it will compare which is having the highest priority. So the priority is 1, P7 will execute. P5 will keep waiting. Okay, so imagine at P, there is a process P8 will come at the fifth millisecond. with the burst time 3. Again, this came with priority 1. Now what will execute? Which process will execute next?
P8.
Again, P8 will execute because the priority is higher. So if the upcoming process, when the process may come anytime and they may leave anytime because it's random, right? When we are creating process, when you are, see, I'm writing something, whenever I'm writing with a laser point, something happening on the background, you'll be able to see that. So each process is executing some work on the background. Now I never know what I'll do next, whether I'll erase this or whether I'll remove this, we never know. But however, some process is working on the background. When a process has been created in the sequence order, this lower priority process will be keep on waiting for its turn. Okay, this is called starvation. Starvation means it will keep on waiting to get the availability. Star means like ideally speaking, star means to get hungry. You want to eat something but you are not getting anything, so you'll starve to death, something like that people will say in English. But the starvation here, it happens is the process need to be finished, but it is not getting time, not getting the processor to get the job done. So this kind of problem is called starvation. Is that clear?
Yes, sir.
Yes, sir.
This is the problem with priority scheduling. When priority scheduling comes, the higher priority keeps on coming and some process will leave in between. The lower priority jobs will keep on serving, or that is called indefinite blocking. That's what we discussed, indefinite blocking or a starvation. Okay, so these are the few important scheduling algorithms that we need to discuss. But there are other scheduling algorithms also. If you have interest in your own time, please explore that in operating systems by Skillbus Scratch. Uh, there is some algorithms like multi-level queue, multi-level priorities. So instead of only one prior, we discussed here only one process, one bus time, one priority. But there could be multiple priority, multi-level scheduling, multiple priority schedulings. So those are the some other variations of the same. But these are the uh, basic approaches that one need to be understand. Okay, that's what we are discussing, all the basic. After round robin scheduling and priority scheduling, there is a multi-level queue. So you can have multiple queues simultaneously. You can execute one for system, one for uh, one for user, one for batch process. You can maintain different queues. You can execute concurrently. Okay, this is called multi-level queue algorithm. There is a multi-level feedback. There is one process, after that next one it will give feedback to one process to other process. This is one Q1. This will, after this Q1, after executing, this will go to Q2. After Q2 it will come to Q3. So multi-level scheduling is also, multi-level feedback queues is also another approach. There are various schedulings, but we will not go into them. These are the basic scheduling algorithms. If you are interested, you explore on your own. Okay, shall we go ahead?
Yes, sir.
So this is something important properties of a CPU scheduling is one of the important things that we need to consider when a process management will happen. Let me discard this. Okay, right. So let us continue our discussion on operations of processes. So we started discussing how a process is, what are the various states of process, what is process control block, what is context switch, and how CPU scheduling is carried out by scheduling different processes. And we tried to understand that round robin scheduling is very efficient in terms of various parameters that if you consider. Let us resume our discussion on processes. Let us discuss the operations on processes. Only two important operations we will discuss. There are many operations you can do on the process, but two important operations is how a process is created, how a process is terminated. Only these two things we will discuss today class, and we will stop. So initially when an operating system including Linux, Unix, Windows. You start with any operating system. Each process will be identified with a unique process identifier called PID. Okay, process identifier. We call that as a process identifier, PID, which is typically an integer number. So, for example, system EMD is the first process that will create in Linux, the process ID 1. Then it will create some login ID process, some Python script process, some shell process. Each process has its own unique process identifier. Okay, 8415, 2808, 3208. If you remember that we studied a process control block. Process control block has the process state and a process number. I will show that. You see this? There is a process number in process control block. Each process has a process number, right? So this process number is called process identifier or process PID. PID. So each process has its own unique identifier will be assigned when a process is created. Okay, so we'll identify that by that PID. Now the process creation, we'll talk about process creation. This is a typical example how a Linux operating system, how the process will create. It looks like a tree, but it's a B tree. Okay, the binary, you cannot say this is binary tree because binary tree will have at most two children, but you can see that there are three children here and it will keep growing as many as children it can have. So, but at the same time, the height will be balanced the way it is organizing. It maintains a data structure of tree data structure. What is the data structure in round robin?
Circular linked list.
Circular queue. It's a queue, right? When a process is added again, it will be added into the queue. Whichever comes first, it will be executed first based on the which it's like you are inserting at one end and deleting at another end, but in a circular fashion. So this is the data structure. What is used in round robin scheduling is circular queue. I think I told you here. You see here circular queue. The ready queue is treated as circular queue. Okay, you can implement circular queue in circular linked list. That is correct only. I'm not saying what you are saying is wrong. The implementation of circular queue you can carry out in circular linked list. That is totally fine. But the more appropriate, appealing word is queue because it's ready queue. Jobs are placed one after the another. We will call them as a queue. So we will implement, the more appropriate word would be circular queue, which you will implement when it comes to implementation. You will use circular linked list only. Okay, is this clear?
Yes, sir.
What is the data structure that you will use in priority scheduling?
Heap.
Does anybody said something?
Sir, a heap, max heap.
Okay, fine. Max heap, min heap, you can use anything. But if you are naive, you don't know anything, you start with priority queue. We discussed priority queue when we are discussing queue. If you recall, there will be a separate queue for the pregnancy or senior citizens. Then normal people has to wait, and the senior citizens will take the higher priority. This is a priority queue, but the way you're implementing priority queue could be using heap. That is another entirely different story. But anyway, so this is a process creation will happen in form of a tree structure. Okay. Now, let us talk about system call. You have to understand what is system call before talking how a process is created. So a process performs an input output by requesting the service through a library function, which is called a system call. So if you assume, if you see that computer in a block diagram, you have a computer hardware. We discussed what is computer hardware in the first class. Your processor, motherboard, your display, RAM, all these things will come as a part of hardware. So the operating system will come in between the hardware and the users. The operating systems, again, if you divide, it will be in kernel mode and user mode. Kernel mode is what is the operating system will execute their own jobs, which will be considered in the kernel mode. User will execute its own user programs like I told that there is some application programs like when I'm running Google Chrome, or my PowerPoint. These are all some application programs. But on the background, Windows is also making my screen looking visible, the graphical user interface, all this provided by the operating system, which are running by system programs. And so there are some user programs which I am manually running it. But all these programs having some library routines. These library routines will be invoked by system calls. See, there is the system calls will come as a part of kernel mode, but the communication happens between the application programs and the operating system is via system calls and library routines. Uh, we studied in your first year C programming, the printf function will print the output. Okay, that is a library routine which is defined in stdio.h. Have you tried to run a program without stdio.h? Have you tried to run a program without stdio.h? Have you tried to print something without stdio.h? Will your program work?
Sir, it says implicit declaration of syntax.
No. Will it work or not? You in your
No,
C
sir.
program, you have written. Try this, okay? Suppose you have written main. Should be in small letter. Uh, you try to write, say, printf ds and os. You compile it and run. Will it work? Will you be
No,
able
sir.
to compile it? Why?
No, sir.
Why you will be not able to compile?
Sir, printf is defined in stdio.h and
Right.
will not include that.
In order to use printf, you need to include a header file, which is also called as a library routine. Okay. You run and check without stdio.h whether you'll be able to print or not. You will encounter errors because this printf function, this is an output function. Print out is an output function which is defined in standard input output header file. Okay, this is a header file. You go and check what is there in header file, and you will be able to see that some library routines has been defined. This library routine will call the system calls to print so that your display will come on the output. Okay, we are not going down and studying the programming languages in so deep in a mission will understand. This is a high level language or a middle level language. So the libraries what has been defined is associated with the programs that we are developing. I am a user, I am writing this program, but this program has been associated with some library routines that is communicated via system calls. So this DS and OS will has to print output on my screen. Then the system call is called to perform some input output requesting for the service through the library function. We call that as a system call. Does this make sense? This diagram makes sense?
Yes, sir.
Okay, so there are various system calls that are associated in an operating system. On background, how a process is created, that we have to understand. But we will not discuss all system calls. But there are everything on the background when operating system does happens through system calls. I already discussed in the beginning of the class once briefly, maybe one slide I would have given what is a system call. but you can check again what is the definition. Let's try to see. The same system call is used to create a process. The same system call on the kernel mode is used to create a process. The system call is called fork. Okay, the system name call, there are various system calls. I'll repeat my statement, please listen carefully. There are various system calls. One such system call is called fork. Okay, the fork is a system call that will help us to create a process. Okay, so what are the other system calls? Uh, if you okay, I will just give a brief idea. The various other system calls are: fork is one system call, ex exit is one system call in order to complete the process that we will discuss. Then file is a system call. It will create files, file descriptors, how to create a file, how to delete a file. Then pipe is a system call. Um then ex execute is a system call. In fact, there is a system call system. There are various system calls. You please explore that. This each system call helps to communicate to the operating system to get the job done. Okay, the operating system uses system calls to get the job done, to perform some input output request, which is defined through our libraries. So when I say writing fork, the fork will help me to create process. So when this program is defined, when a program is defined, when it is dividing into a process, on the background, when it is executing, a process is assigned. A process is created using fork. A system called fork is generated. Okay, when you're turning a program into a process, this is a simple program, a set of instructions, but when it is executed, this program is converted into process for execution. Whenever it is converted into a process, a fork system call is generated. When fork system call is defined to create a process. Is that clear?
Yes, sir.
Okay, so we will take, we are discussing since 1 hour. If you have any doubts so far, you please tell me. Otherwise, we will take 5 minutes break. I will discuss what are the various system calls, that how to create a process, how to terminate a process. I will also demonstrate some examples that I have run in my system, and I took some screenshot. I will show them how it will work after a break. Okay, we'll take a break. Meanwhile, if you have any doubts up to this discussion, you please let me know. Shall we get back, guys?
Yes, sir.
How many are there? 139. Okay. All right. So let us discuss how a process is created using fork. See that a process can create a new process by calling fork. The calling process becomes the parent process, and the created process is called the child process. Both parent and child can execute concurrently. Child process is a duplicate process of the parent process. Get PID, get PPID functions returns the parent ID and parent process ID, something like this. So I wrote a simple C program with sdi.h, and you include this header file unistd. Okay, this is a standard header file. Uh, After that, you define a simple variable x is equal to 0. I called a fork function, and I tried to print what are the values, just to see that what is the value of x. Now, why I'm doing that is because when a fork is called, the parent process and the child process will print something. So the parent process ID and the child process ID, when a fork is called, a process is created. Using fork, you can create a process. It's simply like duplicating in the process. Now, uh, you see this, I am printing only one time. Printf, I am a process. My process ID, you can print process ID using get PID. That's what I have written. Get PID, excuse me. Get PID, get PPID will print its the process ID and parent's process ID. Now I just printed get PID and the value of x. How many times I put printf in this function, in this program? How many times I have written printf? How many times you are seeing, guys? How many times printf is there? Am I mute or what?
No, sir.
Tell me how many times the printf is printed here, I mean written here?
Once.
Only one time, right? When you execute, how many times you should print? Only once. But when I'm executing, I compiled it and I'm executing. You see this, I got two outputs. I am a process with process ID and my value of x is 1. I'm a process with another ID, my value of x is 1. This happened because the fork created and copied the same process. Means the fork, whenever I'm writing a fork, it will create a new process which is similar to its parent's process. Okay, is this clear?
Yes, sir.
The fork is creating the same program which will convert into process. Again, we are calling in terms of fork, so we are creating two processes. So after fork, both the parent and the child can keep running concurrently, and they can fork off other processes. So for example, again, a process tree can result in this way. Root of tree is a special created by operating system during the startup. So initially say that a root of the tree is like bootstrap programming. Once the bootstrap programming is loaded, it will load an operating system. The program in an operating system, what it is loaded, let us assume that it is A. After running some process, A can create B and C. In other words, I can call that A forked B and C, B forked D, E, F. B from B, D, F, uh, uh, the process created, and G created from C, again from D, H and I. You can say that, in other words, A forks B and C, B forks D, E, F, C forks G, D forks H, H forks I. Okay, is this clear? How a process will create again and again using fork, using a simple system called fork. You can expand that tree uh, so much. Okay, now when you fork a process, your parent process and child process is same. Now after creating a process, then the child process, you can reassign some other values, other way of executing that. Then you have to call some other system call, that is exec, that we will discuss later. But the idea to create a process is using fork. Is this clear up to this point?
Yes, sir.
Okay, so you can print clearly. I'll show one more example. Like you can see this SVO dot H and UNISDO dot H. I'm simply printing. I'm not forking. There is no fork, but I'm just trying to print what is the parent process, what is the child process. Uh, if this program has been created from what is, if this process is there, then sorry, if this program is converted into a process, then this process should have been created by someone else. Then I'm just curious to know what is this process ID and my parent ID. Okay, so when I run that, you will be able to see some output, so some integer value for that particular process, and the process that created this process, the parent process, also you can get using get PID and get PPID. Is this make sense what I'm saying?
Yes, sir.
Anyone has want me to repeat the things which I am saying?
So is this a process for the program, for all of the program, or just for, a part of program will be the process?
ज्योमेट्री आजकल बना लेते हैं ये लोग.
It's a one program, right? It's a one program. Main program is one program. It will create one process.
Okay, sir.
And when it is created, but the fork, when it can't create just like that, the property of fork is it will copy from its parents process, then it will redefine its what is the properties that through other some other through other system call. Okay, so initially what happens is the fork, you read this again, what I have defined here, the process can create a new process by calling fork. So in order to create a new process, there should be existing process. One process can create another process. Is that clear up to that point?
Yes, sir.
Using fork system call.
Sir, if
So the
the child
calling,
process,
yeah, the
sir,
calling
if the
process
child
becomes,
process is duplicate of the parent process, then why did the value of x change in the program that you showed?
no, X is not changed now.
Yes, sir.
X is the same here. The process ID is changed. The parent process is different, child process is different. When you fork it, it will create a new process. So the calling process will become parent. The child process, I mean, the created process will come with child. Both parent and child will run concurrently. You can see that using PID and PPID. That's what I have given here. So if this is a program which will convert into a process, then this process should be created by its parents process. You can see their ID also by just printing PPID. Am I making sense?
Yes, sir.
See, you can't. That's what I told. See, A is a fork process that is created by operating system during startup. The root of the tree is A, right? The root of the tree is A. That's what I have clearly written here. See, the root of the tree is a special process created by operating system during startup. Once an operating system loaded in your machine, at the time, so many processes came into your execution. Each process is forking it can create a branch of trees by forking other processes. But after a process is created, it will act as similar to its parent. Both process will work similar fashion. That's what you can see that output. When you call a fork simply, the both parent and child will be the same. It will be the same code. Okay. Initially it will be the same code. After creating a new process, we will change the process information or process details some other way. Does that make sense?
Yes, sir.
How you are changing that process nature using some other system calls. There will be other system calls. I told you excc, that is other system call that we will study in the future. Some other system calls, we will redefine the process execution. But for the process creation, once you need to create a process, you have to call a system called fork. Once a process is created, you can verify whose this process is created by which parent also you can verify, and you can by printing get PID and get PPID, and you can see that their process ID identifier numbers are different. They are not same. Okay. So something like this. So fork system call will create the current process. It will split into two process, parent and child. If you could able to, if you are not able to do it, it will return -1. If the fork is successful, then it will return 0. If the child identifier in the parent returns the child's identifier, means the child's identifier here is its ID. Once the process is created, the child process is created, it will return with its process ID, process identifier. So the child process inherits all the properties, identical copy of memory, CPU registers, all the files that has been opened from parent. Whatever the parent has, all the details are copied exactly to the child. So when you are calling a fork, the same details of process control block information, everything is copied the same into the child process. Execution proceeds concurrently with the instruction from the following fork system call. Is this clear?
Yes, sir.
So let me show another example. So what we did here is, this is a detailed example of understanding the entire fork system call. I defined a simple header files, and I defined a variable process identifier child PID. Then I called a fork system call. The fork system call, if it is returns -1, what it means? If returns -1, if the system call returns -1, it is unsuccessful, right? If it is successful, it returns 0. So if it is -1, then the fail to fork, the child process cannot be created due to some memory issues, due to some other issues. But in otherwise, if it is 0, if child process is 0, then child is created. You can get, you are the child, I mean, you can get the process ID. Otherwise, you can get the parent ID. You can see this. This came little bit later, that's why it's printed at the execution. But once you are compiled and execution, you can able to see that first initially the parent is printed, then after the fork system call is called, then the child is printed. The child will print with a different ID, 3059 3060. Because this is if else program, it will execute only once. Okay, so first parent process is printed. The parent process will come and print its parent ID. Then the fork system call will create its child process. Then child, by the time child is created, the chpid will become 0. Then child will execute. Because this is if else condition, either one of them only will execute. Does this make sense?
Yes, sir.
Run and check these codes in your system, in your Linux system where you run your C programs. You run and verify all the codes that have given. You will have a better understanding of fork. So the fork is a basic system call that will help you to create a process. That's all we want to say. Now, having discussed how to create a process, let us discuss how to terminate a process. How to exit a process. A process termination or orderly termination is through another system called exit. Exit is also another system called like fork. Using this exit system call, we will terminate the process. We can make a process to wait also, that is called wait system call. The parent can execute wait or wait PID with a particular process ID to block the process until its child finishes. So wait system call is also there. In order to uh, exit, in order to avoid the exit, you can make a process to wait before it's finishing, or you can finish, you can terminate that process also. So to finish execution, the child may call exit and the process number. So before exiting, before terminating, it saves the results of argument of exit, closes all the open files connections, deallocates the memory, checks if parent is alive. If parent is alive, hold the results value until the parent requests it wait. In this case, child process does not really die. It enters into a zombie state. Zombie state means it will not die, but it will keep on waiting for the parent request until it removes the wait condition. If parent is not alive, the child terminates. Is this clear? So in order to terminate a process, we will use exit system call. You can make a child to wait for some time using wait system call. If the parent called the child to wait, this call will be, the wait system call is always called by parent. Parent can execute wait until the child finishes. So child will finish. So before child exits the system, it will check whether the parent is alive or not. If it is not alive, it will terminate. Means the parent which is created is not alive, it will terminate. By any chance, if parent is alive and holds the result value until the parent request wait, if it is there, then the child process is not really died and is a zombie state. Anyway, so this is how you will terminate the process. So one example, you can see this. You write a PID assigned x is equal to 1. You called a fork. It will create a process. If PID is not equal to 0, then it will print the value by decrementing the x value. Then you are exiting the process. Else, print the child value of by incrementing the x. Then you exit it. Tell me what is the output of this code? What is the value of parent? What is the value of child? You defined your variable x is equal to 1. You called a fork function. So the program, it will create itself. So when you are going to parent, it will decrement and print that value. It will exit. Then you'll go to the child. Else, if the child is executing, it will increment its value and print the child and exit. So tell me, what is the parent parent x will print? What is the child x will print? Anyone?
0 and 1.
Sir, 0 and 2.
0 and 1, 0 and 2. Okay. Any other answers?
1 0.
1, 0. Okay.
0 and 2.
0 and 2. Oh, okay. So there are various answers, so you are confused. So execute this program and verify, okay, in your leisure time. The parent will print 0 because the initial x value is 0. It will print decrementing 0, but the child value will be printed 2 times because the parent child and the child, you check this is very interesting. That's why I gave this code. The child, ironically, it will print 2 because the value of x, although it is executed by parent, it is not had any effect on the child. It will create, by the time you created the fork, it will create its own child process, and because x value is 1, it will copy all the values, right? So I told you in the previous example, it will copy all the identical copy of the memory CPU registers from the parent. Before the child is decremented, the value of x is 1. The parent process x value is 1, the child process x value is 1. So when the parent is executed, if PID is not equal to 0, means the fork system call, when it returns, if it is 0, then child will go. If it is non-zero value, -1, then the child is not there. If PID is not 0, then the parent will execute. From 1, it will decrement to 0. But once the child is created, once the child is successfully created, at that point of time, the value of x is 1 only. So it will go to the child, it will increment the value of x, it will print 2. Does that make sense what I'm saying, the logic?
Yes, sir.
Anybody want me to repeat the why it is printing 0 and 2? The reason is the x value variable is simply copied into the parent's process and child process. When I'm printing the parent value, this statement will execute. From 1, it will decrement to 0. When a child is executing, PID value will become 0. It will come to the else place. The value of, when this statement is executing, the value of x is 1 because of the fork. Fork will simply copy the values. So the x value will become 2. Okay. Don't confuse with function with values and addressing. You would have studied in C programming. This is slightly different than function calling. You have to see this program as a 2 processes because of the fork system call. Till that fork is called, whatever the values above, it will be the same in both processes. And when it is started executing, based on this condition, it will execute 2 process and you'll get 2 outputs. You run this program and check, and when you get this output, try to understand that till the fork is called, before all the variables will be the same for both parent and child process. And based on the conditions, it will keep executing its own code and the values will change. Is that clear? Shall we go ahead?
Yes, sir.
Yes, sir.
Okay. You can also check, there is another point which is key point of fork. Parent can create his own fork, child also can create its own fork. For example, here in this case, I printed L0, then I created fork. This fork system call will create another function. So the original fork function will continue, then another fork function will create. So L0 will split, after L0, the program will split into 2 processes. That is, say that L1 and L1. You can see that when I'm after forking, when I'm printing L1, it is printing 2 times. After L1, I'm creating again fork. This fork, again it will create the printf. When you are printing by, it will print 4 times. Because both parent and child can continue to fork each other. So the fork, initially it will divide this program into two parts. So you print L0, you call fork, then it will divide into two parts. You will print L1 and L1 will be printed. Then again you fork this L1, again it will create two process. This parent and this child, again it will create two process. So you will get 4 bytes. Okay. You're calling only 2 fork times, but it can create multiple values. It can keep forking each other. Does this make sense?
Yes, sir.
Okay, so let me conclude that. So fork will duplicate the calling process, the result of two process, parent and child. Both will continue to executing from the same point on when it is called. Okay, exit is a orderly program termination, unblocks the waiting parent. Wait is used by the parent, wait for the child to finish its execution. These are the few important operations on the process you need to aware. Okay, so we will discuss this thing, and but before that, you have any doubts up to this slide? You want me to ask any questions? Shall we go ahead?
Yes, sir.
Okay. So inter-process communication is one of the important concept. We will not finish this today, but we will just give a brief idea. We'll discuss in the next class. Inter-process communication is how a process will communicate with other process, how two processes will exchange information with each other. So inter-process communication is a generic term described how two processes exchanging information with each other. So two processes may be running on the same mission or on the different missions. Through inter-process communication, that is IPC mechanisms, one process can communicate with another process using signals and pipes and so on and so forth. Okay, this communication may be exchange of data, or they may be exchanging any information related to process scheduling, not but related to the process schedule work, which they do not destructively the overlap, synchronization. All these issues will come up. The numerous applications that is needed for process to communicate with each other, exchange information or control information, we can achieve this through this system calls. There are various approaches: pipes, signals, message, queues, semaphores, shared memory sockets. Through these various methods, we can make a process communicate with other process. For example, the two fundamental inter-process communication is shared memory and message passing. In shared memory, what will happen is memory which is there is shared between multiple processes. They will exchange information by reading and writing in that shared region. For example, this is like a notice board. The notice board is a shared place. Instead of sending one person to other, instead of me telling that to each and every student in your class, I'll put something on the notice board, which is a shared place. I will share something there. You all will come and verify that. So shared memory will be shared by all the processes. So whatever the process which is reading or writing something can be accessed by other processes, because that is shared between those processes in a cooperative way. There is another method called message passing. Message passing model communication takes place by exchanging the message by with each other. This is one-to-one communication. Okay, so in shared, this is a simple example of communication models. So you have a shared memory. Process A will write something in the shared memory. Process B can also write something on the shared memory. They will have one memory and they will share and read and write in the shared memory. But in message passing, you have a queue maintaining in the kernel, which has nothing to do with sharing. M1, M2, M3, some messages. Process A will access from one side. Process B can be accessed some other side in the memory. It can pass through these memories in a unique way. Also for this, there are some other system calls are used, but it is not a shared, it is one-to-one. Process A will write something and process B will go and read there by sending a message one-to-one passing. Okay, so one such example is called pipes. Pipes is an inter-process communication which allow two processes to send information. You can write this commands, the shell commands that you are using in Linux uses these pipes. For example, when I write who command pipe, this is a pipe symbol, wc minus l, who is a command which generates the output of the user who is currently using the system, which is pipelined to the another command which is a word count, which will give me the length. So who is piped to word. One command is communicating to other command. So one process is communicating to another process through pipe. Okay, so you can run this example and see that initially we define some variables, some constant parameters. I'm calling fork here. If it is not created, then it will create an error. Otherwise, excv is the system call which will execute based on this parameter list of this function to a particular code. You can see this. This is a simple P1 program. When I'm writing head minus 5 P1, which will print first 5 lines 1, 2, 3, 4, 5 up to main. First 5 lines it will print head minus P1. So first 5 lines it will print. This is the command head is given. Now when I write cat p1.c with the pipeline head minus 5, I'll get the same output. Cat p1 is this program. I'm making it into a pipeline. This is one process communicating to other process using pipe. I'm generating another command head minus 5 which will give me the same output. I'm reading cat p1 separately, head minus first 5 lines. When I'm writing two commands, you can communicate this command when it created one process using pipeline to other process, and the output you will get the same. Okay, so pipe is one kind of communication. So it is important to realize that write process and the read process in the pipeline execute concurrently. The buffer it will maintain on the output writer, suspense of writer if the pipe gets full. So the pipe in between, this process will write something, this process will read something, that happens concurrently, that happens continuously. Okay, that's what this meaning. In pipes also there are two versions, named pipe and unnamed pipe. Unnamed pipe is supported by Unix, unnamed pipe which is supported by some other functions. Okay, you can see that I have given some details about named pipes and unnamed pipes. What are the details, how we can define that, you can just go through it. There is also called signal. Signals are generated when an event occurs, like hardware when division by 0, or a kernel, other processes, user process. When something happens, a signal is generated. There are various signals which will communicate from one process to other process. For example, I can create an alarm clock. If there are some error in a bus, signal is generated that will communicate it through the other process. There are some interrupts happen. There is a quit signal. There is a process termination signal. There are many signals that are defined. Many times when you're running a program that doesn't work, you will press Control C, which is a signal interrupt. You are giving an external signal to the computer to stop the program or to stop the process, which is signal given by the user, which indirectly what happens in the background is when you press Control C, signal interrupt is called. Signal interrupt system call is called to generate some interrupt. Okay, so these are the various system calls, signals that are defined in POSIX, which is in Linux operating system. You can see that there are various system calls. Kill, if you put kill a process, you can see that the system calls that are defined with various signals that are defined. When I say that kill minus 9 3432, the process ID with 3432 will be send a signal to kill that process. Then exit system call on the background is called. Okay, kill minus usri is a command signal usri to 3422 You can find the more details about the signal, how a process will communicate with other process is through signals and through pipes. That is one way to look at it. Okay, you can just simply write these commands and verify in your Linux system. You'll be able to understand that in very detailed way. Okay, so for example, I ran this code, include uni std.h alarm 10. Simply run this loop. After 10 seconds, it will print alarm clock. You wait and see. After 10 seconds, you will hear a beep sound. You will hear a alarm sound in your Linux operating system. This is very because of the signal generated by signal alarm is to terminate the process and runs in approximately 10 seconds of a wall clock time. After that, it will terminate the process. So a process will be communicating with each other using these various system calls, various methods. Okay, so pipes signals are one as easiest method, but there will be some issues when you use semaphores or shared memory. When you use them, how a process will synchronize with other process. All those issues we'll discuss in the upcoming class. But today's class, we discussed only how a process is created, how a process is terminated, how a process will communicate with each other. Only 2-3 methods we observed. I will stop here. If you have any doubts in today's class, you please ask. Remaining rest of the discussion will continue in the next class. Meanwhile, I'll upload the slide. You go through the slides. And let me know if you have any doubts. You'll be able to see the slide, CPU scheduling and process management, lecture 19. Please check whether you'll be able to see that or not.
Yes, sir.
Please go through that slide, and if you have any doubts or clarification needed, you let me know. Okay, so I gave you so far only 2 assignments. One is the first assignment, I asked you to explore what are the various operating systems. In the second assignment, I just gave you to implement a doubly linker list. Sorry, circular doubly linker list. Now I'll give you the third assignment. I'm aware that in your lab classes also I asked the faculties to repeat again the data structures that the assignments before assigned. I asked them to repeat one more time. I hope they are making it clear to you before giving an assignments. Again, they are teaching you. That will give you an advantage to revise or to understand in a better way besides what we discussed in the class. So what I would like to tell you is we will try to do some assignments as a part of your internal and the teachers assessment marks. So the concepts which are not feeling confident, whether you are learning through the class or through some other ways, that is totally fine. But try to do and explore in other times as well. So the third assignment which I would like to give you is implement like how you implemented a circular linker list. Implement 2 aspects. One is uh, binary search tree BST that you skipped the class, and you can try to implement AVL tree. Implement binary search tree and AVL trees. That will in turn will help you. I don't know whether it will come or not. So the second part is you can implement the scheduling algorithms also. Few scheduling algorithms that we discussed. Implement them both. Okay, so when you take the user from the user for the CPU algorithms, number of processors, how many processors you have, and arrival time, arrival and burst time. So you should get output waiting time and display the waiting time. Okay, sorry, average waiting time. So this is your third assignment. So please try to do that in your leisure time. Okay. So I'll give you enough deadline. You no need to submit immediately 1 week. I will give you 2 weeks. By 27th, you can submit it. Okay. So take 2 weeks time. So implement a binary search tree and AVL tree, then implement the scheduling algorithms that we discussed in the class. As the slides are already there, you can check the assignment whether you're able to see it or not.
Yes, sir, it is visible.
So
Yes, sir.
you have to do this both by after 2 weeks. So next week there will be no assignment, but however, next week, next Thursday, I will conduct quiz. 2 quiz I will conduct on next Thursday for all the sections. So please come online. Inform to your friends who are not there. Right now there are only 133 students, but your total class strength is 183. So ask others also to come and attempt the quiz. This will be considered as a part of your mid-semester marks. I have to conduct 5 quizzes to consider them as a mid-semester marks. So next week I will conduct 2. Then the subsequent weeks, as we are discussing various concepts, I'll keep conducting quiz. So before your end sem, we will conduct 5 quizzes. So prepare whatever the things that has been discussed so far. That will be next Thursday. We will take 2 quizzes. There will be 2 quizzes. One followed by the another. We will conduct 2 quizzes. Is this clear?
Yes, sir.
Yes, sir.
Okay. So we will stop here. We will continue next week. Go through the slides again. If you have any doubts, please let me know. Anyone has any questions? Okay, if there are no questions, you can leave. We'll stop here.